So I see a stack of homeworks there. Thanks for the quick turnaround on that. Not like you had any choice though, right? Well, it's going to get worse before it gets better. But it will get really good eventually. All right, so let's take a look at your future. Peer into the crystal ball. On Tuesday, you've got quiz number 3. And that is covering the information since our first midterm exam. So that could be on chapter 4 or 5. Because I'm such a kind-hearted guy, I'm going to narrow it down for you. It'll be related to chapter 5. All right? So you are going to need chapter 4 for the upcoming exam. But if you want to focus your study for the quiz, that's going to be stuff from chapter 5. All right, Thursday the 10th, so a week from today, you'll have homework 6A to submit. And then the following class meeting on Tuesday the 15th, you've got both a homework due and an exam. So obviously, you're not going to get homework 6B back before the exam because you're turning it in that day. So if you want to double check on your answers to see if you've got the right idea, I'm willing to help you out with that. You can stop by during my office hours and I'll tell you yes if you've got the right answer or no if you need to make some changes. And as good as our grader is, I don't think he's going to have that Thursday assignment turned around before the exam either. So same thing applies. I think the book has the answers to, what is it, the evens or the odds? Evens. So for odd-numbered problems, if you want to know if you're doing the right thing, you can come and see me, and I'll happily help you out with that. So the exam 2, I'll give you some more details about that when we meet on Tuesday, but essentially it's chapters 4, 5, and 6 on that test. Now, this schedule isn't because I'm mean. It's because there's a certain amount of stuff we have to know in this course, and only a certain number of class periods we have to do it. I think it's 30 lectures through the semester. We're already on class 22. So it's just, there's a standard canon of concepts that students in fluid mechanics have to learn, and so we're getting through it as quickly as possible. It's always a juggle, getting through the material quickly, but at the same time covering things in depth. And my personal preference is to give you a lot of problem-solving opportunities during the lecture so that when you come to the homework problems, you feel like you have some background and can do it. But it just means a really high intensity for the semester. By the end, you'll be exhausted, but you'll be in good shape for hydraulic engineering in the spring. I think that of the 2 courses, students usually feel tired from this one and interested in the second one. So I hope that's the case with each of you as well. Any questions before we get into Chapter 6, Momentum? All right. Well, let's begin with the video. Oh, the lights aren't working today. That's convenient. Let's see, can we turn them on? Yeah, on, but not off. The fire marshal strikes again, I guess. All right. No, I don't think the fire marshal's been by again. This is to introduce the idea of momentum.
Ei paljon painaa. 3 kiloa kappale painaa kenkä. Siinä on kaikki polttoainetta valmis.
Oletko kokeillut lenkillä? Lisääkö juoksuteuvo?
Tuolta sitten niinku hönkää.
Lisa.
So that's I'll have to narrate this since you can't see anything.
Fly.
Right?
I like flying.
This is in Finland. Those are rockets that he's attaching to boots, like ski boots. And he's waddling around with kerosene. Probably below 1. And he's warming up the boots. This is where you expect the explosion, right? Sorry to disappoint you, no explosion.
It's here.
That's the fuel. suit that he's wearing, and then now he's up in a hot air balloon.
Hyvä. This is Finland. Very rough country.
I've yet to check recently if this guy's still
But just
alive.
said that this kind of weather, if you land on the water, you're gonna
That's the sort of thing
die.
that you'd put on.
They are going to use the rubber band.
So he's got a parachute and a wingsuit. And homemade boots. Yeah, this is before GoPros. This was back in 2009. So he was able to achieve level flight. Those wingsuits don't usually generate lift.
Hey. I was fucking first one to do it. I jumped from 2,200 meters and flight until the gas tanks were empty and all pulled 1.5, and I was able to maintain the flight level in 2,000 like a half a minute.
Oh, 2005. I thought it was 2009, so that's really long ago. All right, so what's going on there is that those little jets that he's got on his feet will generate 16 kilograms of thrust for each boot. And he warms it up with a mixture of butane and propane, and then is using kerosene essentially as the fuel for it. And you saw he was tucking in those little bladders. It's about a half a liter per minute for each of the jets. And so he's going through a liter per minute. And that jump was from about 7,000 feet. So those wingsuits, usually what they do is all they can give you is a little bit of forward thrust as you're forward movement as you're falling. I think maybe like a 3-to-1 ratio is what they're good for. But he was able to achieve level flight, as he says, just by increasing the forward movement. And so what we're going to be talking about in Chapter 6 is the fundamentals of forces and moving fluids, and the forces that are required to hold systems steady when there are moving fluids. So this is derived from Newton's second law, and everybody's already familiar with F equals ma. And when we say the sum of the forces, we just mean that if there's more than one force, that we add them together, and you have to have some force in order to resist the acceleration of a mass. Or you can look at it as what force is required to accelerate a mass from a motionless state. Now, acceleration that we're talking about here is local acceleration. So the A, if we dig into that, it's dv dt, change in velocity with respect to time. Now the mass is still there on the outside of the expression, but we could put it on the inside of the expression, and it wouldn't change really what we're saying. We're saying there's a change in velocity with respect to time, and we're multiplying the mass by that acceleration, which is a change in velocity with respect to time. mv is momentum. You may remember that from physics, the idea of a mass that's in motion. It has a certain amount of momentum, and we can apply it, instead of to a single object like a particle, we can apply it to a stream. And remember, our definition of a system is that it's a continually connected body of particles. And its shape can be changing, its direction be changing, but it remains a system. And when we started talking about systems, we also started invoking the idea of keeping very close attention to the location of where the system is relative to a control volume and the control surfaces through which it flows. So here's where we combine it together with Reynolds transport theorem. Reynolds transport theorem, as you remember, had an accumulation term, or storage, and it also had transport. Now, who can remind us what CV and CS stands for? Control volume and control surfaces. And so storage occurs inside of the control volume, and transport occurs through the control surfaces. So when we apply the idea of momentum to Reynolds transport theorem, what we're saying is that inside of the volume, we could have potentially an accumulation of momentum. And momentum, remember, is mass times velocity. And so where is the mass inside of this term? Well, we've got a change in velocity multiplied by a density. And so change in velocity, no, this is volume, excuse me. A change in volume with respect to time, so that's when we're talking about a tank, the liquid level increasing or decreasing. Well, if we multiply that by, and it becomes mass. A change in volume with respect to time is, for example, cubic meters per second. We multiply it by density, which gives us kilograms per second. So kilograms per second, which is a mass flow rate times velocity. So this first term would be related to the accumulation of momentum inside of the control volume. The second term is related to flow of momentum through control surfaces. And remember that dA is talking about a change in cross-sectional area. V here is velocity, so V times A, velocity times area, is volumetric flow rate Q, of course. So Q comes from V times A, and then density times Q is again mass flow rate. So both of these terms have mass flow rate multiplied by velocity. So the second V here, the reason why we don't combine them together is that we want this half of the term to be mass flow rate, and we're multiplying it by velocity. So we can combine the two ideas together. The idea of momentum of a system and the idea of Reynolds transport theorem. And it says that the force required to hold the system steady, which is how we would say the left-hand side of this equation, the force required to hold the system steady, is the sum of the accumulation of momentum inside of the control volume and the flow of momentum through control surfaces. Yes? Yes, it is. Except for that, we would ignore the sign of the velocity when we're calculating the mass flow rate, m dot. Mass flow rate is density times Q, which we could say is density, area times velocity. But mass flow rate is a scalar. It only has magnitude. Mass flow rate will never have direction. And so if there was a negative sign in our velocity, because maybe it's going to the left instead of to the right, we would ignore that when we're calculating the mass flow rate. Otherwise, it's the magnitudes are the same. Here in this first velocity, we are going to be paying very close attention to the direction of that velocity, but not to that one. And normally, this isn't the equation we'll use for actually solving problems. We'll get a different equation that we do all of our substitutions into, but this progression kind of gives us an idea of what that equation is based on. So let's talk about momentum accumulation, because that's kind of a hard thing to think about. It makes sense. We've seen momentum flowing with those jet boots. That's where burning kerosene is turned into exhaust, and exhaust going very quickly out of the jet produces a thrust. But momentum accumulation is a little bit less immediate. So
Energy storage flywheels have very high performance and work on simple principles. To understand their operation, it is best to start with the electric motor generator. An electric motor and generator are really the same machine running in opposite directions. When you put electrical energy into a motor generator, it turns into mechanical energy on the spinning shaft. That's a motor. When you put mechanical energy into the motor generator by spinning the shaft, you can draw electrical energy back out. That's a generator. For an energy storage flywheel, we hook a motor generator up to a wheel. When we put electrical energy into the motor generator, it accelerates the wheel, storing that energy as momentum on the wheel. When we want our electricity back, we let the momentum of the spinning wheel drive the motor generator, regenerating our electricity and slowing the wheel.
All right, so we wouldn't necessarily have to have it be an electrical motor to get that thing spinning. Think about, for example, what if we put paddles or baffles on this flywheel and we dipped it down into a river, and that's what got the thing spinning. Or water coming over a waterfall. Or it could be a jet of air. It could be, for example, a wind turbine spinning the blades of the blades that are connected to it. And so all of those things are examples of momentum being stored temporarily. That spinning flywheel, you can translate that back into harnessable energy, but when we talk about the momentum equation, we're going to usually assume that there's no accumulation of momentum. Most of the times, all of the problems that I'm going to ask you to solve in the homework and on exams, there won't be momentum accumulation, but momentum can be stored, and this expression can handle it if the situation arises. But those circumstances are relatively uncommon. And so what we usually assume is that we have steady flow, meaning that the velocity isn't changing with respect to time, and that the structural parts are stationary. So there isn't any spinning flywheel, there's no like a wind turbine blade that's turning. And if we have zero momentum accumulation, then what that says is that the forces required to hold the system steady are only related to the flow of momentum through the control surfaces. In other words, there's nothing happening inside of the control volume related to the accumulation of momentum. It's just the flow of momentum in and the flow of momentum out. So this is what that Reynolds transport theorem combined with the ideas of the second law simplify down to, that the forces required to hold the system steady can be calculated by considering the flow in and the flow out of momentum through the control surfaces. Now, when we talk about forces here, it's important for us to distinguish between body forces, which are like magnetic forces, electrostatic, and gravitational. Those are one category of forces, but what we're talking about are surface forces. The forces required to hold a system steady are going to require physical contact. And so we may be talking about the force that can be generated from a pair of jet boots. And that was a physical contact with the person that the force was being applied to. Those weren't magnetic forces that were being generated. Those weren't electrostatic forces. So when we use the momentum equation, there has to be some sort of a physical contact. And now this is the equation that you'll use for problem solving. It sort of expands on the idea of flow of momentum through the control surfaces. Let's take a look at what we've got. It says that now this is in the x direction. There's a similar equation for the y direction. But let's just say for the x direction, the forces required to hold the system steady are the outflows minus the inflows. And that's the first thing I'm going to mention to you, is that we have to be really careful not only with the direction of jets, but also whether they're flowing in or out of what we define as our control surfaces. So here the first term is it's the mass flow rate out and then multiplied by the velocity out in the x direction. Now, jets may have a direction other than just pure horizontal. And so if it is a velocity in a direction other than purely in the x direction, we have to find the x component of the velocity. And so the sign and also the magnitude of velocity is important, but when it comes to the mass flow rate, it's only the magnitude. So it's the jet flows out minus the flows in. We can also write the same thing in the y direction, and all that changes is that it would be the velocity out in the y minus the velocity in the y. The mass flow rate term stays the same regardless of the direction, as long as it's out versus in. So I've already emphasized this, that sign convention is important, and what we'll assume is that any jet movement to the right is positive x, and anything that's going up is positive y. That'll be our standard convention. Also, let's talk about in versus out. If we draw a control volume around some part that is interacting with a flowing fluid, then in means a stream that's going towards and through that control surface, and out is out of the control surface. Kind of hard to define what out is without using the word out. Let's practice that. Okay, so here, if we have a jet coming in and going out, you'll notice that in the x direction, the flow out, the velocity out is positive because it's to the right, and the velocity in, we would also put a positive sign in front of both the in velocity and the out velocity here. Now here, it's a little bit differently because you can see that there's a stream that's coming in from the left, this inflow here. So the inflow at 2 would have a negative sign there for the velocity. In addition to whatever magnitude that's got, the sign of it would be negative. And then the y direction is going to be negative there. Okay, so this one is for you. Label, in the same way that above that I've labeled the outflows and the inflows, tell me for the outs and the ins whether it's positive or negative. Yeah. Okay, so it's positive in the x direction. What about velocity 1, which we know is in? What about in the y direction? It's negative because it has a downward component to it, so minus. Okay, stream 2, velocity 2, is it in or an out? It's in, right? It's coming in. And in the x direction, positive or negative? It's negative because it's to the left. Velocity 2 is an in. And in the y direction, also negative because it's downward. And then 3 is our out, so velocity 3 is an out. And for the x direction, is it positive or negative? Positive because it's to the right. And velocity 3, which is an out. In the y direction, positive or negative? In y, it's up, so it's positive, right? So pretty straightforward as long as you take the time to think of it. But sometimes just even the most obvious thing, if you don't methodically consider whether it's to the left or to the right, whether it's in or whether it's out, it's easy to substitute the wrong value into the formula if you don't take a moment and just look at the direction and whether it's an in and an out, and positive, negative. Is there a question in the back? Okay. We're going to apply some ideas when we are solving problems, and one of the general principles that can help you out during problem solving is to sketch where the control volume is and enclose where things are changing. So take, for instance, what if you had a jet of water coming out of a fire hose? Okay, so there's a jet of water coming out of a fire hose and it comes towards a wedge. What's going to happen when that jet reaches the wedge? It's going to be split and deflected, right? So the jet of water is going to start going in different directions. So now it was only in the x direction to begin with, and now this jet of water has both an x component and a y component. And so when I say select a control volume, what you want to do is you want to enclose where some sort of a change in momentum is occurring. So we would, in this instance, select our control volume to enclose that wedge. And the things that we keep track of, the in and the out, here would be the fluid stream coming in, and here would be two fluid streams coming out. And then we would apply the ideas of what are their mass flow rates, what are their velocities, and so on. Sometimes we'll combine concepts together. So there may be other governing equations besides just the momentum equation. Sometimes we'll have to also use the continuity relationship, or there can be a combination problem where it's Bernoulli's problem. For example, if you wanted to find out what is the velocity of this jet, it could be that you're given the pressure inside of the hose, and you have to use that pressure inside of the hose to find out the velocity of the jet as it comes out. So we can sort of mix and match different ideas together. Momentum accumulation, remember, you should be on your lookout for that because it's going to change how you apply the momentum equation if there is accumulation, but there won't be on the problems that we solve. So let's take this balloon example as our first try to find out what force is required to hold the system steady. Here, the pressure inside the balloon is being expressed in kind of an unusual way. Rather than being given as a pressure, it's being expressed as a depth, or you could think of it as a head. They're saying that the pressure inside the balloon is 0.4 meters of water. So what you can do with that is you can use water's unit weight and that distance that they're describing to find out what is the pressure inside the balloon in terms of newtons per meter squared. They're telling us the nozzle diameter of that balloon, which you can of course use to find the cross-sectional area, and the air density. And so we have to find out, in a situation like this, using Bernoulli's equation, what's going to be the velocity of the air as it goes out. And then once we know the velocity, use the momentum equation to find the force required to hold the system steady. Because if we don't apply that force F, you can see the way that it's configured, then the balloon is going to start shooting to the right. Just the air that's coming out. Maybe you've even played around with balloons before, letting go of them, and then they fly all crazy around in wild directions. Well, this one's connected to a straw and a string, so it would just be moving in a straight line. We need to know what force is required to hold the system steady. One last thing to say about the pressure is when the air comes out of the balloon, instantly that stream of air has the pressure as the same pressure as the gases that surround it. And so the pressure, gauge pressure, is 0 of the jet that comes out, but the pressure on the inside of the balloon is 0.4 meters of water. Good. Did you guys get the right velocity? Okay, good. So if we use Bernoulli's equation with the pressure 1 of 3924 newtons per meter squared, or approximately that, depending on what you use for the unit weight of water, that pressure, the interpretation of that is they're saying the pressure inside the balloon is the same pressure that would be experienced at a depth of 0.4 meters of water. And so what we can use is the hydrostatic equation to calculate what's the pressure in terms of newtons per meter squared at a depth of 0.4 meters of water. Because that's going to be the units we have to have in order to substitute into Bernoulli's. And so we assume that the velocity of the gas at 1 is 0 because the balloon is contracting and the wind that's coming out of it presumably is coming from the edges of the balloon, whereas the wind in the middle is essentially stationary. Okay, so that's why we said let V1 be 0. And we say that the P2 is 0 because it's surrounded by air, atmospheric air. And so as soon as it comes out of the balloon, it has the same pressure as the surrounding air. So P2 is 0, V1 is 0. Substitute that into Bernoulli's equation. And even if you had written it in terms of head instead of in terms of pressure, you'd get the same velocity, I think, of 80.87 meters per second. Okay, so that's only half of the question, though. Once we have the velocity, we need to put that into the momentum equation. So let's draw our control surfaces so that what's happening is inside of the control volume. So there's nothing coming into the control volume. There's just flow out. So the equation is going to simplify, and there's only one force that's being applied. So instead of saying the sum of the forces in the x direction, we can just say the force in the x direction is, there's no in, there's just out. So we need to find the mass flow rate out and multiply it by the velocity out in the x direction. And this, fortunately, that jet only has an x component. So all of the velocity that we calculated just now is in the x direction, except, remember, we have to be really careful about signs here. So when you do the substitution, you're going to want to call that negative 80 point, what did we say it was? 87? 87 meters per second, because the jet's to the left. So in order to calculate the F, we have to find the mass flow rate. And the mass flow rate you can get from this. It's the density times the area times the velocity. Okay, so in the first part of the problem, you're finding the velocity of the gas is 80.87, and that's to the left. So we have to be really careful about substituting in a negative value when we are calculating the forces. So, you know, this negative 80.87 meters per second is because the jet's to the left. Calculate the mass flow rate by the density of the fluid in question. We get in the habit of the fluid usually being water, that it's really easy. Anytime you see density, just to write 1,000. But you have to remember the jet here is a jet of water, a jet of air. There, I did it. I fell into the trap. So you calculate the cross-sectional area of the balloon, the velocity times density. That gives us the mass flow rate. And what about the units? Did the units work out? Do you get newtons when you have kilogram meter per second squared? So it is newtons that arises out of mass times velocity. So it works out. Now the negative sign of this means that the force has to be applied to the left. And that's what the picture kind of implied. But sometimes we will get in the habit of just always putting the force like this, saying here's the F sub x, and then the direction of the force we would indicate at the end of the problem with a negative sign there. Or you would put in words the force required is to the left. You know, there are a lot of ways to communicate the direction of the force, and you have to do it one of the ways, in a quiz or an exam or a homework. So if it's asking find the force required to hold the system steady, it's not enough to find the magnitude. You also have to clearly indicate the direction that's required, either with the drawing or in words or with the sign. There has to be, that's part of the right answer. Okay, so any questions about this example? Yes, so if this was my handout and I started with a drawing, like the drawing already showed it to the left, I would say in words you could write at the end to the left as indicated or something. not for what we've got pictured.
So like you could ask us a question like what direction is force going? Use that.
You'll have some problems where there's a black box. Let's say you've got something where there's water coming in and then water going out here, and then maybe another stream coming in here, where it's going to be a lot less obvious what forces are required to hold the system steady. And so in situations where you've got multiple jet streams, it's not going to be as easy as this. And so in the problem you'll say the force in the x direction is some magnitude, and you'll have to indicate to the left, to the right. So you can put the sketch of the force, like the sign convention, on the drawing itself of the problem, but then when you calculate the magnitude, also indicate that whether it's to the left, to the right, or as shown in the drawing. And if it ended up being a force to the left, then you could say here's F sub x, and then in your answer you wouldn't want to put the negative value, because then negative and to the left would actually mean that the force is to the right. So just pay attention to not doing like a double negative kind of situation, and it'll be fine. All right, there's one more kind of video example I want to show you today related to an even newer development compared to that wingsuit, which can't dim the lights. Let's see.
When the first video of this invention appeared on the internet, some people just couldn't believe it was real. But it is. It's the Flyboard Air from French jet ski champion Frank Zapata and Zapata Racing. Having previously developed a hugely popular original flyboard, a similar-looking water-powered craft, Zapata Racing has taken a major step forward with the Flyboard Air prototype. This marvel of engineering can achieve 10 minutes of self-controlled flight at altitudes of up to 10,000 feet with a top speed of just over 92 miles per hour. That's 3 times higher than the world's tallest building. The Flyboard Air operates using 4 joystick-controlled jet turbine engines with a backpack fuel tank. Along with the rider's balancing ability, an onboard computer helps stabilize the platform during flight. On April 2nd, 2016, off the coast of France, Zapata shattered the Guinness World Record for the farthest hoverboard flight. With the record to beat set at 275.9 meters, Zapata flew the Flyboard Air an astonishing 2,252.4 meters in a single flight. Though the Flyboard Air was originally intended to highlight the company's abilities, public excitement has led them to consider making a commercial version.
For the sake of human safety. All right, so let's do some calculations related to that. Let's assume that the rider is 80 kilograms and that the board and the fuel together have a mass of 20 kilograms. And I looked at like the size of the backpack, and it seemed like maybe in the backpack, if the flight itself is 4 or 5 minutes long, it would be tough to have much more than, like in a backpack, maybe 10 liters of fuel maybe. So let's just, like, as a starting point, they sometimes call these back-of-the-envelope calculations, where it's just sort of like a really rough estimation to give you an order of magnitude. Let's assume that he's burning 2 kilograms per minute of fuel. Now the fuel-to-air ratio we're going to need to calculate the mass flow rate that's coming out of the jet. And when it comes to kerosene, if you look up the chemical formula of kerosene and do a combustion reaction, and then you convert it from stoichiometry, like the molar ratio, to the mass ratio, it's about 1 kilogram of fuel uses about 3.5 kilograms of air. So 1 kilogram of fuel, in other words, is going to give you 4.5 kilograms of exhaust. So what I want us to try and calculate is how fast does the actual exhaust jet have to be in order to allow for level flight. So let's just do a little sketch here. We've got the board and it's got wind coming out of it. There's a guy, I'm not even going to do a stick figure, it'd be too bad. I'm just going to say it's 100 kilograms. Okay, so what we're trying to do is produce lift or thrust that can go upward with the force that's equivalent to 100 kilograms for level flight. Now in reality, he has to do more than that in order to be able to go upward. But at a minimum, what jet velocity must be achieved? And so we're going to do the forces in the y direction, and just for simplicity, let's assume that there is only flow out and that there's no flow in. Because if there's flow in, then that's actually going to increase the velocity that's required even more. But let's just assume that they have like a really diffuse inlet for the wind, or maybe the incoming air is being sucked from the front rather than vertically, because that would improve the lift characteristics. But anyways, all right. So calculate what is the velocity that's required. When we convert from mass to force, and you can calculate the mass flow rate of the exhaust that's coming out of the bottom of the flyboard air. Okay, so the first thing, just to find out the force that's required to support this 100 kilogram load, it's going to be 981 newtons. And I make a note here that the best case scenario for us is that there's no flow in, there's only flow out. Because if there's flow in, then that actually reduces the amount of thrust force that's available. So, you know, the air that's coming in, when we look at the momentum equation, that would actually reduce the amount of thrust that's being generated. So just for our first work through, we'll assume that the inflow velocity and the inflow rate is 0. Okay, so we want to convert the mass flow rate of the fuel into the mass flow rate of the exhaust. We know it's burning 2 kilograms per minute, and there's 60 seconds in a minute, so now we've got kilograms per second of fuel. But what's coming out of the bottom of that is a mixture of fuel and air after combustion. And so for every 1 kilogram of fuel that's burned, it's 4.5 kilograms of exhaust. So the mass flow rate of what's coming out of the bottom of this thing would be 1.5 kilograms per second. And so therefore, if we put it into the momentum equation, the force that's required, the mass flow rate that's calculated, then that says the velocity of the gas coming out would have to be 6,540 meters per second. And that's at a minimum, assuming that there's no gases coming in to reduce that. Because if we had an inflow term, then that would subtract from the force that's being generated by the outflow term. So, I mean, this seems kind of ridiculously high. Probably the exit velocity isn't that high, and so what that tells us is it must be burning fuel at a rate that's greater than what I had originally assumed. My guess, I don't have any specifications, but my initial guess was it was burning 2 kilograms of fuel per minute. Probably it's burning a lot more fuel than that. It might also be that it's not kerosene. This fuel-to-air ratio is for kerosene. If he's burning a specialized fuel that uses more air, then for every kilogram of fuel that's being burned, there would be more thrust. So it's an interesting example. I wish I knew more about it, but it illustrates the principles in any case. The calendar is packed, so let's take one more look at what's going on. All right, I told you the hint that the quiz you have on Tuesday is going to be covering Chapter 5. That's continuity relationships. Chapter 5. Then on Thursday, your first momentum momentum homework is due. Then the Tuesday after that, our exam and the second homework assignment. Things will settle down after Thanksgiving. All right? Have a good day. I'll see you next time.